everyone, today we are going to learn Chapter 8, Rotational of Rigid Body. So let's look at the first subtopic, Rotational Kinematics. We code for the first angular displacement, theta. So what is the angular displacement? So angular displacement is defined as an angle through which a point or line has been rotated in a specified direction about a specified axis. We can write as theta is equal to S over R. Theta stands for the angular displacement, S is the arc length, and R is the radius. The unit for the angular displacement is radian, and the other unit is degree and revolution. We need to know also the conversion factor. One revolution is equal to 2 pi radian and equal to 360 degree. The direction of the angular displacement, theta, is positive if it rotates in the anti-clockwise direction, and the sign is negative if it rotates in the clockwise direction. Next, we have average angular velocity. Average angular velocity is the rate of change of angular displacement, and we can write as omega is equal to delta theta divided by delta t. The delta theta is equal to the change of angular displacement, means that theta final minus theta initial divided by t final minus t initial, and the SI unit for the average angular velocity is the radian per second. Instantaneous angular velocity is the rate of change of angular displacement at a particular time or at that moment, and we can write as the omega is equal to the d theta over dt. And other unit for the angular velocity is the revolution per minute, or we can write as revolution per minute or RPM. And 1 RPM is equal to the 2 pi over 60 radian per second. The direction of the angular velocity can be determined by using right-hand grid rule. The thumb shows the direction of the angular velocity, and the curved finger shows the direction of the rotation. Next, we have average angular acceleration. It's the rate of change of angular velocity. We can write as average alpha is equal to delta omega divided by delta t. Delta omega is equal to the change of angular velocity, or you can write as omega 2 minus omega 1 divided by t2 minus t1, or omega final minus omega initial divided by t2 or t final minus t initial. The SI unit for the angular acceleration is radian per second square. The instantaneous angular acceleration is the rate of change of angular velocity at particular time, or we can write as alpha is equal to the dw over dt. And if the rotation is speeding up, alpha and omega is the same direction, and if the rotation is slowing down, the alpha and omega have the opposite direction, or we call it the deceleration. For the speeding up, we call it the acceleration. The table shows the symbols used in linear kinematics and rotational kinematics. So for the displacement, we have the symbol for the linear is S, and the rotational is theta. So the relation between the linear and the rotational S is equal to r theta. For the initial velocity, we have u for the linear motion, and for the rotational motion, we have omega naught. And the relation is u is equal to r omega naught. For the final velocity, we have v, and for the rotational motion, we have omega. And we got v is equal to r omega for the relation. And tangential acceleration, or for the linear motion, the symbol is a, but for the rotational motion, we have alpha. And at, or tangential acceleration, is equal to the r alpha. Okay, next we have the comparison of equation of linear and rotational motion with a constant acceleration. As you know, we have the four main equation that we have learned before in chapter 2. So now the comparison between the linear motion and the rotational motion, we get the alpha, or angular acceleration, is also constant. And for the first equation, we have omega is equal to omega naught plus alpha t, and s equal to ut plus half at square for the linear motion. And for the rotational motion, we have theta is equal to omega naught t plus half alpha t square. And then next we have omega square and equal to the omega naught square plus 2 alpha theta. And the last one is theta is equal to half omega plus omega naught multiplied by t. So this equation is very familiar, okay, to the linear motion. The difference is only the symbol for the rotational motion. Let's look at example 1. A rigid body rotates about a fixed axis through a point in the body. With a uniform angular velocity, we have 6 revolutions per minute. So for the initial angular velocity, you need to convert into radian per second first. So we have 600 revolution per minute. So convert to the radian per second means you need to times 2 pi over 60, because 1 revolution is equal to 2 pi, and minutes convert to second, divide by 60, and we have 20 pi radian per second for the initial velocity. And then the velocity then decreases at a constant retardations to 300 revolution per minute in 6 seconds. So you need to convert also the final angular velocity. So equal to 300 revolution per minute. So convert into radian per second. 300 times 2 pi divide 60, and then you will get 10 pi radian per second. Okay, what we have here is t, 6 seconds. So let's do the first questions. A. Okay, calculate or determine the angular acceleration. So for the angular acceleration, you need to use the equation of omega is equal to omega naught plus alpha t, and then substitute the value for omega and omega naught that we already convert into radian per second. So omega we have 10 pi, and the final angular velocity we have 20 pi plus alpha and t is 6 seconds. So you rearrange the equation and we get the alpha or angular acceleration is equal to minus 5.2 radian per second square. For second questions, determine the number of revolution the body has turned through in 6 seconds. So for this question, you're going to use the second equation that we have theta is equal to omega naught t plus half alpha t squared. Now you need to find or calculate the number of revolution, which is theta. So we just substitute the value. Omega naught we have 20 pi and t we have 6 seconds plus half alpha we got from the first questions which is minus 5.2 and times t is 6 seconds. Don't forget to square t and we get 90 pi radian. So the question need the number of revolution. So you need to convert into revolution. So one revolution is equal to 2 pi radian. Instead we get theta is equal to 45 revolution. For the question C, determine the extra time needed by the body to come to a stop if it continues to slow down at the same rate. So come to stop means that the final velocity for this question is equal to 0. Final angular velocity is equal to 0. So for this question, we're going to use the first equation. Omega is equal to omega naught plus alpha t, and then substitute the value for the final velocity. We have 0, and the initial velocity you need to take from the this one. The final angular velocity will become the initial angular velocity before it stops. So omega naught is equal to 10 pi plus alpha is equal to minus 5.2, same. For the first from the first equation because decrease at a constant. So the acceleration or angular acceleration is equal minus 5.2 and times t. So we get t is equal to 6.0 seconds. Second questions. A car is traveling with a velocity of 17 meters per second. So here we have you on a straight horizontal highway. The wheels of the car have a radius of 48 centimeters. So 48 centimeters you need to convert into a meter first. So 10 to the power of minus 2 meters. If the car then speeds up with an acceleration of 2 meters per second square for 5 seconds and calculate the number of revolution. So now you need to calculate the theta. Theta of the wheels during this period. So we're going to use the third equation. Theta is equal to omega naught t plus half alpha t squared. Means that you need to calculate the omega naught and alpha to solve this question. But from the question given that u, a and t, so you need to calculate the omega naught first. And then we need to refer to the relation between the linear kinematics and rotational kinematics. So here we have u is equal to r omega naught. Please recall back this is the relation between the linear kinematics and the rotational kinematics. So from this you can calculate the omega naught, and then we rearrange or we substitute the value for u. We have 17 and equal to r, we have 48 centimeter. So don't forget to SI unit in meter, so 0.48 and then times omega naught, and then we can calculate the omega naught. We get 35.4 radian per second. And then for the alpha or angular acceleration, also we need to calculate from the coefficient. We have the relation between A, acceleration, and the angular acceleration. A is equal to R alpha. So we have acceleration is 2 meter per second and equal to R, we have 0.48 and times alpha. Okay, calculate the price, the calculator. We got alpha is equal to 4.17 radian per second square. And you can substitute the value of omega naught and alpha into this equation to calculate the number of revolution. And then substitute omega naught, we get 35.4 times t. T is 5 seconds, and then plus half. Alpha is 4.17 and times t is 6 seconds. Don't forget to square c and then press the calculator. You will get theta is equal to 229 radians. So don't forget to convert radians to revolution because the question state the number of revolution. So theta is equal to 229 radians. So convert into revolution. So 1 revolution equal to 2 pi radian. So radian we can cancel out, and then we have 36.5 revolution. So this is the answer for question A, 36.5 revolution. For question B, calculate the angular speed on the wheel after 5 seconds. So for this question, we use the equation of omega equal to omega naught plus alpha t, and then substitute the value for omega naught. We have omega naught is equal to 35.4. Okay, we already calculated on the first questions, and then plus alpha is 4.17 times t is 5 seconds, and then you will get omega is equal to 56.3 radian per second.